Welcome to Talkin Science, where we dive into the stories making headlines in the world of science and space. I'm Matt Miller. Dr. Brad Tucker is here. Brad, happy Tuesday.
How's it going?
Really well, my friend. Let's get the headlines in this, the 49th week of 2021. LCRD launches to prove the laser communication concept. Exoplanet Cannonball, a ball of rock filled with iron, is orbiting a red dwarf. And the closest supermassive black holes that will collide soon have been discovered.
This is Trekzone's Talkin Science.
And don't forget, Trekzone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus Trekzone's on Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow and subscribe. Brad, too, on social media, at btucker22 on Twitter, and Dr. Brad Tucker on Facebook. Brad, it's our 150th episode, an incredible achievement for this side hustle that we have, and with just one more regular episode left this season after today.
It goes fast, 150, I guess, so it just seems like yesterday.
It absolutely does. Let's get into the show. NASA has bought another 3 Crew Dragon flights even, from SpaceX, hedging their bets against more Starliner delays, Brad.
Yeah, this is purely Starliner delay driven, that they always said that they wanted redundancies, hence the funding of both SpaceX and Boeing, because at least hopefully one would work, and if both work, they'd have the backup. But since Boeing is clearly delayed, they still haven't even done their orbital tests, and that's pushed back sometime to next year. They don't want to wait around for Boeing to get ready without having those options of flight access, hence the securing of 3 additional SpaceX crew flights. So definitely not a good sign for Boeing yet again, unfortunately, in this space.
Yeah, exactly right. Well, last week, the inaugural Space Industry Association of Australia Southern Space Symposium brought together participants from across Australia to outline achievements and discuss progress in a variety of fields, all to highlight our growing space sector. Brad, it's one topic that we'd love to cover here at Talkin Science.
It was very driven by the industry. Who's doing what are the plans? It's nice to also have these events that are in person. Unfortunately, I wasn't able to attend in person, but there is growing interest across a variety of sectors in industry on this, not just defense, not just the space agency. That's where also the space agency released their Earth observations roadmap that we talked about last week. So it's definitely an area that we'll see more activity in over the coming decade.
Very cool. Looking forward to that one here at Talkin Science. Well, space lasers, Brad. That leads our stories of the week. NASA's Laser Communications Relay Demonstration mission launched a few days ago, and it's the current buzz of the town. We've spoken recently about it, but remind us again what the plan is here, Brad.
How can we communicate and transfer data via lasers? And we have this picture of lasers of just being these beams of light. Well, that's actually what a radio wave is. Just because you can't see the radio wave, it is a beam of light. It's just a different energy. Where with the laser, the idea is with the energy that you could put into the laser, that you can actually embed information, i.e. data. And if you can transfer data via laser, you can transfer a lot of it a lot faster. And that's the name of the game here. Higher, faster data transfer speeds to space, in particular to satellites, and really the moon. As humans go to the moon, there's going to be a lot of data, video, photos, all that sort of stuff needing to come back.
Now, you say fast. It's like going from dial-up to broadband, really, isn't it? Unless, of course, you have the NBN here in Australia.
Yeah, look, it is a dramatic jump. We're talking about 100 or so times faster than what you can do for radio waves. It's not even a comparison to the speeds. And it's not to say this will make radio communication obsolete. That is not the point at all. Radio waves have the benefit of some of that deep space stuff that lasers will still have and be affected by in terms of the power and energy you can generate. What we're talking about here is the data volume of nearby. We're not going to be sending high-def video back from Jupiter, but we do want it from the moon, and we want a lot of it in real time, because that's the key here. radio waves, you can still wait for that data to be transferred, if you have to wait a day or two for all the data to download. With the human space flights, they're going to want all of that stuff to be coming back in essentially a relatively short time frame, i.e. instantaneously. So how can you send that back in those time frames? Well, this is probably the way that you can do it.
Now, as I say, LCDR has launched, and that's in geosynchronous orbit. Artemis 2 in 2024 will have an optical communication system on board to extend the range test by a fair way, with the hope that this will be the viable option, as you say, for communications with a base on the moon, on the red planet, further out, just something a little faster and a little closer to real time, as you mentioned, Brad.
Yeah, it's really that stepping stone. They want to test in geosynchronous orbit. Okay, it works. We can do that. Then let's do it, as you said, to the moon with Artemis 2, and then further on. And that's how this is going to be as they roll out this technology. How far can we use it? What are the speeds? What system is also best? There's not just one system designed. There are different systems being designed that will be tested. We are building one at Mount Shermla where I work. So all of these will be working at different capabilities to see who's doing what works the best, what is the best system. And it may be a combination of systems, right? It may be this works really well for the moon, this works well for better satellites. This is a really exciting new technology that a lot of people are jumping on board and testing. And it is the way of the future of communication in space. But because of that, all of these proper tests and system requirement checks need to be done.
There's a practical reason for this too, Brad, with dozens of satellite mega constellations and commercial space launches pretty much all but eating up the precious radio frequency spectrum. So not just that real time, not just those tangible benefits as well, but getting away from potential radio clashes and stuff like that.
Yeah, it's noisy, so you want to make sure you find your signal the best, and this is only going to be the only thing done via lasers, at least in the next decade or two. So it's not that you're worried about interference or another system coming on board that would create those issues as well. And also the interference you get is also just different because of the dispersion in the beam. So radio waves spread over distance. Well, so does a laser. It just does it a lot less than a radio wave. So those issues are also mitigated. So again, yet another benefit that you have over the traditional communication.
Well, next up, Brad, a small planet that's as dense as pure iron has been discovered, hurtling around a nearby red dwarf like a cannonball.
This is a very dense, almost the remnant or the inside of a planet. When we talk a lot about Mercury in this way, that Mercury in some ways could almost be talked about as just the core of a planet, that the outer layer or layers has been stripped away, and you're really just left with this kind of solid iron-rich thing. And this is what this appears to be. It's a what we call these ultra-fast planets orbiting very close to its star, just like Mercury, but this is much closer than Mercury. And maybe this is the big sign about how these very, very inner, close, rocky planets behave. Maybe they are not really able to form some of those outer layers like Venus or Mars or Earth, and that what only can happen is the inside, so to speak, the inner layer cores can only survive.
Now, it's the smallest exoplanet that astronomers have been able to get the precise measurements of, and it takes just 8 hours to orbit its planet, its parent even. Do we know if this is a stable or even a sustainable orbit, Brad?
Well, look, potentially, one of the problems with always measuring these ultra-fast planets is, when you're looking at something that's 8 hours, it's actually too often going around. We're definitely biased towards finding shorter period planets because we like to see the confirmation of the transit multiple times. But so, when you're waiting 10, 30 days, okay, you only have to observe it for a few hours every 10 or 30 days. It's actually relatively easy to do. But if you need to observe the transit for a short period every 8 hours, that actually makes it really tricky. There's also other instrumental artifacts and, issues that an instrument has, in this case measured by tests, that you have to take into account. And these are also really short. So, to get that timing down of minutes on the scale of hours is actually really hard. So this is kind of one of the impressive measurements of this, is how close and how quick this period is. And then this obviously raises the question of, we think it could be a stable orbit and it should be a stable orbit, but just how stable are they? Has it migrated? Was it always like this? It is around a red dwarf, so it's a much smaller star than our sun. So maybe it is possible with a star this size rather than a more sun-like star, but still a very interesting discovery just because the extreme nature of this entire system.
Now, it's not the densest exoplanet discovered, but it is heavier than any of the rocky planets in our solar system. It's likely to be a bigger version of Mercury, as you said, Brad.
Yeah, a really big Mercury iron core. And so it's the combination of everything. You have a very dense planet, very hot, very fast period. So it's a very extreme case of it. Think about it this way, right? Even our moon orbits the Earth every 27.8, 28 days. This is orbiting every 8 hours. We're talking about something that is orbiting 3 times faster than our planet spins around on its axis. This is a very extreme system. So the fact that this thing exists at all is kind of I think the shock, and the ability to get this measurement shows the power of some of these space telescopes, of how precise they can be in these measurements.
Well, lastly this week, Brad, astronomers have discovered a pair of supermassive black holes that are the closest to Earth ever observed, and they're on a collision course with each other.
And this is kind of the exciting result, is that, we like supermassive black holes. We also like seeing them merge. Now, generally, when we see this, either they're very far apart, and so they're going to merge in the scale of billions of years or hundreds of millions of years, or they essentially have already started to merge. Here, as you're seeing now, you can clearly see the 2 supermassive black hole centers that are slowly starting to merge. And this gives us a good chance to start to measuring the dynamics, the physics, the interaction between these 2 objects, and then compare it to how it happens with stellar mass black holes, the smaller mass black holes that we see merge and create gravitational waves.
Well, the previous closest supermassive black hole record was 470 million light years away from Earth. Now we're down to 89 million light years. That's still a lot. That's a lot closer, Brad, but there's still a few galaxies over. Will we have a frontish row seat of a potential merging anytime soon?
Yeah, look, it's not that close to us, but it's close enough that you can resolve the inside, and that's the exciting thing. Generally, it is either too close and nothing really is happening, or too far away and you can't see clearly the potentially 2 galaxies or the 2 supermassive black holes in the galaxy. So the fact that it's kind of in that sweet spot is really what's exciting. Now, it will merge soon, but soon is still millions of years, so it's not something to hold your breath on.
Or put a calendar reservation in for.
Exactly.
Well, could there be more of these binary black holes out there, Brad?
Look, and we definitely think so. We think this is how black holes happen. We think the supermassive black holes merge just like their smaller stellar mass counterparts to form bigger ones. There's no reason they shouldn't. There's no reason they can't. And we want to see this growth. We want to see how these bigger ones come into play. And so measuring the different stages of sizes of black holes, the merging rates of black holes, and how they merge really gives us clues to the physics, exactly what happens. And, so far, we've really started to learn a lot in the past few years about how these things behave, from the small ones with gravitational waves to the intermediate mass ones to now these supermassive black hole ones, and images like the Event Horizon Telescope. So we're really changing now how and our understanding of black holes. And it's not that we're necessarily been wrong in our thinking, but it's getting that solid data to confirm the ideas, the theories, and the calculations that show exactly how they behave. And that's the exciting thing when something is this close to get more information about.
One last question on this one, Brad. If these are supermassive black holes and they're going to collide, what's next in the scale?
I feel super duper massive black holes, but that's an unofficial term. And that's kind of, and this is actually kind of the weird thing, is we don't have a clear upper limit to supermassive black holes. It just gets bigger. We know they can get to a few billion times the mass of our sun. Where's the ceiling? Where it happens? And where is the boundary between really where a supermassive black hole is and an intermediate mass black hole? And that's actually where there's a lot of interest, is we want to work actually towards the middle now. We want to see where the supermassive black holes go to the intermediate ones, and that relates to the stellar ones, because that's the key to see how big they are, how they grow, and really how we can get so many big supermassive black holes in the early universe when there wasn't stuff there. So maybe there's another phase. Maybe we should just call it black hole and, age group or size group. I don't know. I still like super duper.
One thing I love about Talkin Science is, Brad, is that I can bring the funny questions in and you bring it right back down to reality and some super serious science. I think it is brilliant. Super duper black holes. That's what we're going to be calling them on Talkin Science from now on.
I'm fine with that.
Well, just before we go, a look back on a Talkin Science interview from this year. Dr. Graham Walker beamed in March to discuss how he creates engaging science communications to interest the public. During the interview, I asked him about the outreach program that he runs with Questacon. How do you tailor a program to keep everyone interested?
It's a good question. Interest is it's a really intriguing thing. Interest is one of the things I studied in my PhD, which kind of looked at emotional engagement in science communication and actually looking at, well, what are those different emotions? So I guess you've kind of got that side, the kind of more psychological side of engagement, and then you've got the actual program. And I think one good example I can give, the program, or in fact, highly biased, warning everyone, is a program on circus. And we run a master's program where students come and do their master's, and as their fieldwork in that master's program, they go out and run the science circus. Now, a couple of important things about the circus is it takes science to where people are. It doesn't rely on people, coming to the science. It actually tours around regional Australia.
That one is out now, of course. Catch it via the card on a YouTube video or on the official watch page on the website. Brad, great to pick apart the stories of the week with you. We'll do it all again for the final regular show of 2021 next week.
Great.